Energy storage is one of the essential missing pieces in the quest for a future that is almost entirely powered by wind and solar. Claims are made that we can use battery storage or hydro storage or some other form to make it happen in the end. Minute Physics and Real Engineering have created 2 videos where they try to calculate the likelihood of us building this essential storage infrastructure. Bear in mind that these are 2 very popular science channels on YouTube with combined more than 4.5 million subscribers. So these channels are quite influential. Earlier this week, a friend of mine asked me to look at 2 videos which they have produced in tandem. In the meanwhile, both videos have been seen more than 500,000 times. Let's examine if their calculations are correct. Or did they miss something?
Over the last 20 years, a slew of ever lighter, ever more powerful rechargeable batteries has enabled the rise of smartphones, miniature high-definition cameras, drones, commercially competitive electric cars, wireless headphones, and so on. So are we moving towards a future where the entire planet is battery-powered?
Probably not, but let's see what Minute Physics has to tell us.
There are 2 big factors that'll determine that possibility. 1, how light and energy dense we can make batteries.
And 2, whether we'll even be able to physically manufacture enough batteries.
These are 2 very important questions indeed. First, we are going to finish the Minute Physics video and see whether it contains any errors. And then we are going to examine the Real Engineering video in order to see whether their math is correct.
The current standard for lightweight, rechargeable, and commercially safe batteries uses lithium and graphite on one side with a variety of options for the other side, often lithium cobalt oxide.
Lithium is the lowest common denominator, and we are going to find out whether we produce enough of it later in this video.
More likely is that we end up combining pretty good batteries with supercapacitors, fuel cells, hydropower, and other mechanical energy storage types, and airplanes will probably always have to use some sort of hydrocarbon fuel.
Here Minute Physics concedes that batteries alone aren't going to power the world. Perhaps the capacitor can fill a gap, and pump storage as well, but as Clack et al. Demonstrated in their rebuttal to the 100% WWS roadmap, these possibilities are very limited. And it is indeed highly unlikely that airplanes and large ships will become decarbonized entirely. We may be able to propel them with synthesized fuels, or perhaps with small modular reactors in the case of ships, but that's probably as good as it gets.
Or maybe we'll finally figure out fusion.
Let's start with nuclear fission. There's a lot of really cool stuff happening in the world of nuclear fission right now. Generation 4 reactors are being developed as we speak. Let's see what Real Engineering has to tell us.
As technology continues to intermingle with our lives and the world's dependence on fossil fuels dwindles, the humble battery has grown in importance. The market for lithium-ion batteries, the most popular battery type, has grown by an average of 21% every year since 2004, and that's expected to accelerate even further as Tesla and Panasonic's joint venture, the Gigafactory, a massive lithium-ion battery factory that will double current output, begins to ramp up production, and as renewable energy continues to get cheaper. So are we moving towards a future where the entire planet is battery powered?
Now that's the key question, isn't it? But is it going to be addressed adequately?
There are 2 big factors that will determine that possibility.
1, how light and energy dense we can make batteries.
And 2, whether we'll even be able to physically manufacture enough batteries.
Now, Real Engineering is going to try to answer this question based on the premise that batteries are made by battery factories. So if we have enough battery factories, we are good. Now this is a non sequitur, and I will explain why later.
The Gigafactory in Nevada is expected to manufacture 35 gigawatt hours of battery cells a year by 2020, enough to supply 500,000 vehicles a year. That's pretty impressive, but last year, 72.1 million cars were built along with 22.5 million commercial vehicles, consisting mostly of large trucks and buses. How many gigafactories would we need to replace current fossil fuel car manufacturing with all electric cars? Let's assume each car would use the same battery as the Tesla Model 3. We do not have a confirmed battery for the Model 3 yet, but Musk has stated it will be between 60 and 70 kilowatt hours, so let's go with 65. Even with Tesla's smallest planned battery, we would need 134 gigafactories to produce 72.1 million Model 3s per year, and this isn't even counting the 22.5 million commercial vehicles produced each year. I'm not convinced that a Tesla truck is really feasible with current battery densities, since the 3000 kilowatt hour of battery power necessary would take about 20 tons of lithium-ion batteries.
But we're not at the theoretical limit yet, Brian. If battery technology continues to improve, something like a lithium-sulfur battery of that capacity could be as light as 6 tons.
But regardless, in order to build enough 3000 kilowatt hour batteries, we would need another 20 gigafactories just to replace the 250,000 trucks being built in North America alone. That's not even including the 22.25 million commercial vehicles in the world, which would likely bring the total required gigafactories to replace current automotive production to around 300.
So this is where we go off course. If 20 gigafactories putting out 35 gigawatt hours of batteries a year are required to build 250,000 trucks in North America, we would need 1,929 gigafactories for 22.25 million commercial vehicles with 3,000 kilowatt hours a year. And I question whether this 3,000 kilowatt hour figure is accurate, because that's 50 times more than a car, and you can see why later on.
So just replacing automotive production alone would be a monumental task that Tesla simply cannot take on alone, and Musk's estimate of 100 gigafactories is a bit inaccurate with current production targets, but Musk did state during the 2016 Tesla shareholder meeting that they could potentially triple the planned output of the gigafactory if the demand was there. If that is true, 100 gigafactories seems fairly accurate.
Now there is some ambiguity here. First, 100 gigafactories producing 10,000 gigawatt hours of batteries will be more than sufficient to create 72 million Teslas. In fact, we could do it with 47 gigafactories. However, it won't be enough to create all the necessary 3,000 kilowatt-hour batteries for the 22.25 million commercial vehicles. In fact, we would be short roughly 622 gigafactories. How about cumulative upkeep? The current low-tech batteries only last for about 5 to 7 years before they start failing, and then you really need to replace them. It is safe to assume that the battery will start degrading gradually, and after 100,000 kilometers, the battery may have lost about 10 to 20% of its initial capacity. When does one start to consider replacing a battery pack? After 200,000 kilometers? 300,000? It's not entirely unthinkable that by then the car has already been scrapped. Another question will be how large is the overall failure rate? Is it 1 in 10, 1 in 50, or 1 in 100? In all honesty, I don't know. I have looked, but it seems that this information is not being disclosed. The issue with all these questions is that they are theoretical. For instance, can we build 100 gigafactories? Are there even plans to build 100 gigafactories? As it stands, we have 1. Even more important is the corollary question. Do we produce enough materials to facilitate such a growth in the first place? More on that later.
Tesla has equally grand ambitions of providing battery storage for the grid and home too, and have allocated production to the tune of 50 gigawatt hours a year to run alongside the 35 gigawatt hour cell production for this purpose. Let's analyse how many gigafactories the grid would need to become stable under 100% renewable energy, keeping in mind that we do not need to produce all of this in 1 year. The European Renewable Energy Council optimistically targeted 2050 as the year that Europe could generate 100% of its energy with renewable energy. So let's say we have 33 years to produce the required storage. That statistic of a 1 gigawatt hour battery supporting New York for 270 seconds should give you an idea of how much battery storage will be needed to support a city. But not all the electricity will come from battery. Much of it will come directly from the power source as it's being generated. There really is no reason why we could not rely completely on renewable energy supported by batteries and pumped storage.
Hold on, this is a leap of faith and shouldn't be inserted unless there's some kind of substantiation in front of it. Right now, all we have to work with is 50 gigawatt hours of additional battery production by Tesla. There is no reason to accept this premise at all. Pumped storage is also inserted without any form of prior substantiation, and recent academic rebuttals to the solution project have shown that hydro as a form of pumped storage cannot be scaled as advertised nor as needed.
And the European Renewable Energy Council has suggested this breakdown of energy sources to reach that goal by 2050. Let's first look at that suggested wind power capacity at 462 gigawatts. We can estimate how much storage this would need by taking a look at Australia's new Hornsdale wind farm, which is supported by the world's largest battery storage facility, consisting of 129 megawatt hours of storage provided by the Tesla Power Pack. This storage is there to allow the 99 wind turbines, with a capacity of 315 megawatts, to provide stable power to the grid, removing the problems of variable wind speeds. Scaling that 315 megawatts to 462 gigawatts would require 1,467 times more storage, or 189 gigawatt hours of storage. A single gigafactory could produce that in less than 4 years. Hydro, biomass, concentrated solar power and geothermal would require no battery storage, as they are relatively stable over the course of a day. Ocean energy would require similar storage to wind. Concentrated solar power can store its energy in molten salt, and geothermal in particular has an incredibly stable capacity factor, even beating coal. The capacity factor tells us an energy source's ability to deliver on its maximum possible output. Solar has one of the lowest capacity factors over the course of a single day because it generates 0% of its potential power at night, and thus requires the most energy storage. As a case study for how much storage we would need here, we can take Tesla's project in Hawaii to provide the isolated community of Kauai with a solar-powered microgrid. The Kauai project consists of a 13 megawatt solar farm paired with a 52 megawatt hour battery installation. Already we can see that the ratio of batteries to power capacity is much higher, and this is on a tropical island in the Pacific Ocean. Europe would likely need a higher capacity to make up for less sun, which would likely reduce the ratio of capacity to storage. This may skew results. Nevertheless, scaling that 13 megawatt solar farm to 962 gigawatts would require 74,000 times more storage, or 3,848 gigawatt hours of storage. Adding in our storage needs for wind and ocean, we get a total of 4,064 gigawatt hours for Europe alone. Europe currently makes up about 13.3% of the world's energy demand. So an estimate, full of assumptions, for the battery storage the world would need is 30,556 gigawatt hours.
Here things get downright contradictory. First, we are working off the premise that the European Renewable Energy Council is a credible source, which I will dispute out of hand. But let's examine the figures. 462 gigawatts of wind power for Europe and 962 gigawatts of solar power for Europe, and a total of 4,064 gigawatt hours of storage. Let's focus on the generation capacity first. If we extrapolate all figures based on the 13.3%, we get the following figures. 3,474 gigawatts of wind capacity to power the world and 7,233 gigawatts of solar capacity to power the world. If I apply an optimistic capacity factor of 0.25 to solar and 0.35 to wind, we get a total annual energy generation capacity of 32,894 terawatt hours by 2050. And this is assuming that we maintain a status quo in energy demand all over the planet. This is woefully inadequate when we want the battery to power the world. In fact, this is only reaching up to 15, maybe 20% of the world's total energy balance. If this is the best we can do, we are in deep trouble, and we are going to learn why in a minute.
That much battery storage would allow New York to run at peak usage for 95 days straight without any additional power, which would take 18.5 gigafactories 33 years to manufacture, and with current prices per kilowatt hour of storage would cost $3.8 trillion. This lines up neatly with Tesla's goal to build 10 to 20 gigafactories. With 18 gigafactories running at current production targets, Tesla would be able to produce enough cars to overtake Ford's current market share in motor vehicles with 9 million vehicles, and allow Tesla to produce enough battery storage to help transition the world to a 100% renewable grid over the next 33 years.
If you, as a viewer, have become confused, that is not strange, because the initial question was, are we moving towards a future where the entire planet is battery powered? And now we have to make do with 9 million plus Teslas and a transition to a 100% renewable grid over the next 33 years. First of all, a 100% renewable grid is something entirely different than a 100% renewable planet, which was not adequately qualified in the initial premise and has only just been stated in the final sentence of the regular/non-ad video. Let's talk about material production, for instance, steel, copper, aluminium, or consider fertilizer, concrete and bricks. What about those processes? Are we going to electrify them too? If we would categorize energy, we would see that electricity is only 1/10, perhaps 1/8 of the primary energy consumption of the planet. So when someone says, can we power the entire planet with batteries? I want to know whether we can do the same with the processes I earlier mentioned. Most of these processes get their energy from either burning coal or gas, and believe me, things can get pretty hot when you force more oxygen onto the mix. Additionally, we are not going to decarbonize airplanes or ships with batteries. It is unlikely that trucks will be decarbonized as well, unless we find a way to synthesize their fuels using high-temperature heat sources like molten salt reactors. But let's consider the projection from the US Energy Information Administration. As you can see, they project that our energy demand will go up from what it is today, about 170,000 terawatt hours, up to 250,000, perhaps even 300,000 terawatt hours by the year 2050. And this is all a function of an increasing world population and the subsequent need for more energy, not just for luxury electricity, which you can store in batteries for phones and laptops and such like, but mainly for potable water creation and distribution, animal husbandry, cultivating farmlands and delivering food to people in need. As of yet, no one has answered the question where all the additional energy comes from that is being put into these batteries. Generating 32,000 terawatt hours with wind and solar is not enough when it comes to defeating the influence of fossil fuels. Did you notice that we need about 30,000 gigawatt hours of storage for 32,000 terawatt hours of annual electricity generation. Suppose we would build an electricity mix of 250,000 terawatt hours. Would we then also need 234,000 gigawatt hours of battery storage? If that's the case, we would need an additional 71 gigafactories to make it there in time before 2050. So that's 793 gigafactories, churning out a grand total of 79,300 gigawatt hours worth of batteries each year, most of which will be for trucks and buses. Remember, 3,000 kilowatt hours a pop. I have this funny feeling something is off here. Here's a question for you. How much lithium do you think we need? Here's an excerpt from my book, The Non-Solutions Project. Consider these simple figures. The current worldwide annual output of batteries is about 43 gigawatt hours per year. Projected worldwide output of batteries is 117 gigawatt hours. The annual lithium production rate is about 32 to 36,000 tons. The amount of lithium used in batteries is 31%. Requirement of lithium per kilowatt hour is 259 grams. And we reach this conclusion by dividing 36,000 metric tons by 100 and multiplying it with 31, thus getting 11,160 metric tons used for batteries. Subsequently, we divide the 11,160 metric tons by 43 gigawatt hours, and then you get 259 metric tons per gigawatt hour. So at 259 metric tons per gigawatt hour of battery capacity and at a production rate of 79,300 gigawatt hours, we would need an annual lithium production of 20.5 million tons of lithium. That's 570 times more lithium than we currently extract. Good luck with that. Even if we would be able to build 72 million 65 kilowatt hour Teslas, we would still need 1.2 million tons of lithium per year. This is still 34 times more than we produce today. The creators of these two videos, Real Engineering and Minute Physics, seem to forget how big of a jump it is from 43 gigawatt hours of battery production, which we currently have, to 4,700 gigawatt hours, which is needed to build 72 million electric cars in a year. That's a factor of 110. So the initial question has not been answered well enough. The future role for batteries may be bigger than it is now, but it won't be sufficient to feed a growing population and power the necessary progress into the future. Both videos are incomplete and therefore misleading and should be adjusted or retracted, as they will undoubtedly be used to influence people and perhaps even policymakers to pursue a future that doesn't exist. You cannot power the world with batteries. You could store some energy in batteries, but that energy has to be generated elsewhere. And secondly, you can build as many factories as you want, but if the extraction rate of lithium falls behind what you need, you cannot build those batteries. And if you, like me, value double checking and want to help people understand what is happening on this planet, consider becoming a patron on my Patreon page and help me take care of my kids while I make this content for you to watch and share with others. Thank you for watching.